Hello, and welcome to the FireVoxel tutorials. In this tutorial, we will introduce FireVoxel's tool for generating the image-derived input function. We will describe the algorithm used in FireVoxel to derive the input function and demonstrate its application in Dynamic Contrast Enhanced MRI and Dynamic PET. In dynamic imaging, such as Dynamic Contrast Enhanced MRI and CT and Dynamic PET, serial images are acquired and analyzed to derive functional information about organs and tissues. The analysis of dynamic datasets is often performed using compartmental modeling. Compartmental models represent organs and tissues as sets of interconnected, homogeneous, instantly mixed chambers. To derive quantitative information, compartmental models require input functions driving the system. The input function is usually determined as the time activity curve, or contrast concentration curve, in a feeding blood vessel. It can be derived from the dynamic images by selecting voxels based on the characteristics of their time activity curves. We will first review the main steps of FireVoxel's algorithm for generating the image-derived input function. The algorithm consists of two stages, seeding and vessel tracking. In the seeding stage, the algorithm finds a location with the tallest peak in the time activity curve within a user-defined rectangular region enclosing the vessel. In the vessel tracking stage, this seed is used to initialize the search for nearby voxels with similar time activity curves. These voxels form a vessel tracking region, and its average time activity curve serves as the image-derived input function. We will now describe each stage in greater detail. In the first seeding stage, the user defines a rectangular vector region of interest R over the feeding vessel. Within this region, the algorithm considers all three-dimensional spheres with centers inside the region R and diameters d in a user-specified interval. For each sphere, the average time activity curve is constructed by averaging all voxel curves within the sphere. The sphere with the tallest peak is selected, and its location and time activity curve are used as the seed to initialize the next step. At the start of the second stage, a three-dimensional tracking region is initialized with the seed sphere as the starting location. The reference time activity curve to which all new curves will be compared during tracking is set equal to the seed curve. The algorithm has two modes, regular and adaptive. In regular mode, the reference curve remains equal to the seed curve throughout vessel tracking. In adaptive mode, the reference curve is set equal to the average curve over the tracking region and is updated on every iteration. Next, vessel tracking begins iterations. At each step, the algorithm considers all spheres adjacent to the current tracking region and selects the sphere with the time activity curve most similar to the reference curve based on the following three criteria. First, the peak height of the new curve must exceed the user-specified threshold percentage of the reference curve peak. Second, the peak time of the new curve must be within the time tolerance interval of the reference curve peak time. And finally, if the first two conditions are met, the new curve must yield the smallest difference between itself and the reference curve, expressed as an L norm. The sphere that satisfies these three conditions is then added to the tracking region. In adaptive mode, the reference curve is updated to the average curve of the newly expanded tracking region. This sequence is repeated until the user-defined vessel length is reached or tracking fails. After vessel tracking is finished, the image-derived input function is determined as the average time activity curve over the filled voxels in the tracking region. To demonstrate the image-derived input function tool in action, we will use Abdominal Dynamic Contrast Enhanced MRI. We can display our dataset in three orthogonal projections and play it as a dynamic experiment. This dataset consists of 26 three-dimensional coronal images acquired with the temporal resolution of 4.6 seconds after a bolus injection of gadolinium-based contrast agent. We can also preview the time course of the aortic signal using the Voxel Time Activity Browser. We will determine the input function from the abdominal aorta at the level of the renal arteries. Before using the input function tool, we first need to draw a vector region of interest over the vessel. The tool will not work without this step. Use the Construct Vector ROI tool to draw a rectangular region over the aorta. This region may be 2 or 3-dimensional. To monitor the next steps, let's open the Layer Control panel. Now, on the main menu, select 4D Processing, Image-Derived Input function. This will open a panel with this operation's parameters. The top part of the panel, labeled Curve Similarity, contains parameters used to compare the time activity curves with the reference curve. The peak time tolerance and the peak signal low threshold specify the tolerance settings for comparison of the peak time and magnitude, respectively. The L1 or L2 norm can be selected to evaluate the difference between the candidate curves and the reference curve. The middle part of the panel sets the vessel tracking parameters. The bidirectional tracking option allows selecting the entire tracking region or only its part. The algorithm always tracks the vessel in both directions away from the seed sphere. But if bidirectional option is unchecked, only the longer arm of the tracking region is retained. If bidirectional option is checked, both arms of the tracking region are included. The adaptive option toggles between regular and adaptive modes. The minimum and maximum diameters set the limits for the diameters of the candidate spheres at every tracking step to account for possible variation of the vessel width over the tracking region. The maximum length sets the limit of each arm of the tracking region. The maximum turn limits the angle by which the direction of the tracking region can change from one tracking step to the next. This ensures that the tracking region follows a smooth course along the vessel. To estimate vessel diameters, lengths, and angles, use the Construct Polyline tool to draw vector lines with 1 or 2 segments. To estimate vessel width, click the tool icon, then click once on one side of the vessel, move the mouse, and hold the crosshair over the other side to see the length measurement. To estimate an angle, click the tool icon, then click twice along the vessel and hold the cursor above the vessel's new direction to see the angle measurement. In the lower part of the panel, labeled Output, we can specify which voxels within the tracking region will be used to derive the input function. Use the Higher Signal Voxels menu to select a percentage of voxels or a volume in cubic millimeters. Next, check the box labeled Tracking Map to create a color-coded map of the tracking region, showing its growth at each step. This map will be created in addition to the tracking region mask and may be helpful in understanding the tracking process and making any necessary adjustments. Once these parameters are set, click OK. A new layer labeled IDIF and containing the vessel tracking mask will be created. The average signal of the IDIF region will be automatically displayed in the ROI Stats 4D panel. This curve can be copied to clipboard or saved as a text file. The tracking map will be placed in a layer labeled Tracking Info. By default, the tracking map is displayed in the rainbow color map, with the seed sphere shown in black and other colors indicating areas added at each tracking step. The results of vessel tracking can be saved with the FireVoxel document. just like any other region of interest layers. Next, we will derive the input function in prostate MRI. This dynamic contrast-enhanced dataset has 21 time points with approximately 6-second temporal resolution. To generate the input function, we will first draw a vector ROI over the right external iliac artery. Open the Input Function tool and select the diameter of 5 mm and the length of 20 mm. And here is the arterial input function, and the corresponding red tracking region extends along the artery. Let's now draw a vector ROI over the external iliac vein and generate the input function with the same parameters as before. The blue tracking region is placed in the vein. Now, we will draw another vector ROI that includes both the artery and the vein, and generate the input function. This green tracking region is again placed in the artery. Let's open the Layer Control panel and plot all three input functions together. We can see the green curve is nearly identical to the red curve derived with a more carefully drawn vector ROI. If an input function is derived from a location where arteries and veins are in close proximity, mixing of their signals may be minimized by careful drawing of the vector regions of interest and by adjusting the curve similarity parameters such as the time and magnitude tolerances. Finally, we will demonstrate using the Input Function tool in Dynamic PET. This image set was acquired with Pittsburgh Compound B, or PiB, the tracer that targets beta amyloid and is used in imaging of Alzheimer's disease. This dataset consists of 34 frames with time intervals ranging from 15 seconds during the first minute to 30 seconds and longer at later times. We will determine the input function in the internal carotid artery. Let's load a previously saved vector region of interest and visualize it in 3 orthogonal projections. Next, open the Input Function tool to select the parameters and generate the input function. The resulting tracking map shows 5 tracking steps. The input function curve has the shape that reflects a bolus injection of tracer, with a well-defined first-pass peak. This curve can now be saved and used for dynamic modeling of tracer uptake. This concludes this tutorial on FireVoxel's Image-Derived Input Function tool. This operation enables fast and reproducible derivation of the input function for compartmental modeling across different imaging modalities. For more information, please visit our website. Thank you.